This is Stylianos. I'm a physics teacher for ATS in Align, and in this video we'll try to solve question 1 from the 2022 AP exam for electromagnetism. This is the first page of the exam, and as we scroll down for the question, we see the basic constants that we will need, the unit prefixes, the basic rules that we use for the AP exams, some basic calculus and geometry tips. And here's our first question. As you probably know, we need to solve the question in 15 minutes. We'll try to do as fast as possible. However, we'll give thorough explanation of what we're doing in every step. Now, what is very, very important is a clear understanding of the diagram. We have basically a sphere and a shell. Probably there will be some electric charge in the internal sphere and the external shell. And this is what the question tells us, that we have a non-conducting sphere. In some cases this could be important. Actually, this will probably be important because this means that the charge is spread out evenly, or probably evenly, in the whole surface of the sphere, with uniform volume density, so the charge is spread out evenly, is surrounded by a thin concentric conducting spherical shell, as we see in the view. The sphere has a charge of minus q, so actually I was wrong to put positive charge there. We have negative charge that we can consider it to be minus q, and the shell has a value of charge plus 3q. My guess is that this means that the questions will be sooner or later, what is the charge on the inner surface of the shell and on the outer surface of the shell. We know that the internal radius is r and the radius for the shell is 4r. And we need to determine the charge on the outer surface of the shell. So there is a charge on the inner surface and a charge on the outer surface of the shell. Now we need to mention that since we have a conducting shell, some charge will be attracted to the minus q that is in the center. So the charge that it is on the inner shell has the same value and opposite to the charge that it is inside, so it is plus q. And we need to mention that the total charge on the shell is the inner plus the outer. The total charge is plus 3q. The inner we found it to be plus q, and the outer charge will have a value that it is plus 2q, which is the final answer for part A. We can proceed to part B, where we need to use Gauss's law in order to find an expression for the charge at a distance r less than the capital R. So we need to find an expression for the electric field inside the conducting sphere. And we need to express the values in the given quantities. Now, Gauss's law, we can find it also in the rules page, states that the area integration for the electric field is equal to the enclosed charge on a Gaussian surface divided by the constant epsilon 0. Now, what does this mean for our sphere? This sphere has a charge that it is, actually I should have said that this is a negative charge if I'm not mistaken. Yes, minus q in total. So on this sphere there is a lot of negative charge. The total value is negative q. But if we consider that there is a Gaussian surface of a radius small r, we need to figure out what is the value of the electric field at the surface of this Gaussian surface, of this Gaussian sphere. For this, we think that there is there is a charge density that it is the charge of the sphere divided by the volume of the sphere. The volume of the sphere is 4 over 3 pi capital R to the power of 3. But at the same time, because this charge density is uniform, it is equal to the enclosed charge divided by the volume of the small sphere, which is 4 over 3 pi small r to the power of 3. Now, the charge is negative, so I should have placed a minus over there. And if we take this part of the equation, we will try to solve for the Q enclosed. The 4 over 3's and the pi are cancelled, and what remains is that the enclosed charge on the small sphere is negative Q times R to the power of 3 divided by capital R to the power of 3. So now we are ready to proceed to Gauss's law. The integral, the surface integral, the area integral for the sphere is the area of the sphere, which is 4 pi r squared, and because this is the small sphere, we are talking about the small r. The enclosed charge is minus q times r to the power of 3 divided by r to the power of 3. So the intensity of the electric field is minus q times r divided by 4 pi, I forgot the epsilon 0 in the previous step, so 4 pi epsilon 0 times r to the power of 3. And this is an expression for the electric field at a distance small r away from the center of the small sphere. So we see that the electric field increases, the value of the electric field increases linearly as a function for the distance away from the center of the sphere. And we can proceed to part C, where we have the electric field at the surface of the sphere being equal to 8 Newton per Coulomb, and we need to find the electric field at a distance 2r. Now, this means that we need to find an expression for the electric field away from the sphere. Now, if you want, you can say that the electric field away from the small sphere is the usual expression for the electric field, which is kq over r squared. If you have the time, maybe you should prove it. Basically, you should say that away from the small sphere, again, we'll try to apply Gauss's law. So the area integration is equal to q enclosed over epsilon 0. Since we are at a distance 2r, the charge that it is enclosed is only the charge of the sphere, so minus q. So again, electric field times 4 pi r squared is equal minus q over epsilon 0, and from this we bring again that the electric field is minus q over 4 pi epsilon 0 r squared, which is the same expression that we had before. And from this we understand that the electric field and the distance are inversely proportional. Actually, the distance to the power of 2 is is the factor that will help us calculate the electric field at that distance. So if we double the distance, we can say that since the distance is increased by a factor of 2, this means that the electric field will be decreased by a factor of 2 to the power of 2, so it will be decreased 4 times. So the electric field, it will be 8 over 4, it will be 2 Newton per Coulomb, which is our final answer for part C. And after this, we can move on to part D, where we need to find an expression for the potential difference for the potential difference between the outer surface of the sphere and the inner surface of the cell, and we need to express these values in Q and R and physical constants. Now, we can remember that the electric field is minus derivative of potential with respect to the distance, or that the electric potential is equal minus integral of E dx. And we need to consider this integration. In this case, it's a little bit better to say dr instead of dx. And the values that we need is the surface of the sphere, which is r, and 4r. Now, the electric field that we will use for this is the value of the electric field that we found in part C. So minus q over 4 pi epsilon 0 r squared for r until 4r. The minuses cancel out, and we bring that the change of potential is equal q over 4 pi epsilon naught. Now the integral for r to the power of negative 2 between r and 4r is q over 4 pi epsilon naught r to the power of negative 1 over negative 1. And we need to replace the value for r is equal capital R to r is equal 4r. This means that the delta V equals q over 4 pi epsilon naught. We said that this is 1 over r, but the values that we'll get is 1 over 4r minus 1 over r. This has a negative value, negative 3 over 4r. However, since we need the absolute value of this, at the end we will say that the delta V for these surfaces is 3 over 4 q over 4 pi, actually the 4 is already there, actually 4 times 4 brings a 16, 16 pi epsilon 0 multiplied by capital R, which is the final value. We can check if we made any errors, but I think we are correct. And we move on to part E, where we need a graph of the electric field and later a graph of the potential with respect to the distance r. Now, the electric field shouldn't be too difficult. We proved on part B that the electric field is minus q times distance divided by 4 pi epsilon 0 times r to the power of 3. Let me bring this here. The electric field for distance is smaller than capital R is minus q times 4 pi epsilon naught times r to the power of 3 multiplied by the distance. This reminds us that the electric field, which is the value on the y-axis, and the distance, which is the value on the x-axis, are linearly proportional with a negative on the start. So we will have a linear proportional function. If the minus was not there, it would mean that the electric field increases linearly with the distance, but because we have the minus, we'll get that the value increases, but on the negative axis. Later, on part C, I think, we proved that the electric field is inversely proportional to the distance to the power of 2 and still negative, so the value will be decreasing, but inversely proportional to the distance to the power of 2, so somehow like this. It will not get the value 0 because we're not going to infinity, but it will receive a value that will tend to become 0. Somehow like this. The basic part is to show that there is a curve. And the same thing will be happening for distance more than 4r, but the difference is that the total value of the electric field will be positive because the total value of the charge is plus 2q, so there will be a value for the electric field. We don't know exactly what will be the value, and we don't have the time to calculate it, and again it will be decreasing inversely proportionally to the distance to the power of 2. So again, it is important to show that there is a curve that tends to become 0 at a distance away from the sphere. So somehow like this. I don't think that this is too difficult, but the next part is somehow a little bit challenging, in my opinion, where we need to explain what happens to the electric potential. Now, the basic rule for the electric potential, if you remember, it is kq over the distance, but at the same time we need to remember that the electric field is negative derivative of the potential. According to this, since on the center of the sphere we have, on the small sphere we have negative charge, there will be a value for the potential that will be negative. Now, since the electric field, the value of the electric field actually, let me show it here, the value of the electric field increases, that is on the negative axis. This means that the electric field that increases as a value, the slope, the electric field is the slope of the voltage. So the value of the voltage will get the opposite of what is happening to the electric field. Since the value increases, the value of the voltage will decrease. So the voltage will be decreasing on a curve, somehow like this. And again, as we said that the electric field is kq over r, it will tend to become 0, but it will not become 0 at a distance r. It will become 0 at a distance that it is infinity. So the voltage will be a curve that decreases and will tend to become 0. However, later, along at a distance 4r, we have positive charge, so later we will have a value that is positive, and again it will be decreasing as a function of the distance. So in between we need a we need a continuous line, not a constant line, we need a continuous line that somehow connects these two graphs, but it is not a straight line like I drew it, so I will modify a little bit my first line. It will be somehow like this, with a tendency to become a straight line, and then somehow like this, the electric potential increasing and then decreasing as a function of the distance. So the graph should be approximately like this, and make sure that the line in the middle is not exactly straight, but the curve is showing like there is a curve somehow like this, and later somehow like that. That's it, I think, for part 1. On the next video we'll solve part 2. Feel free to share your comments, and have a good time studying physics. Thank you for watching.